My name is Neha Runta, and I'm going to be talking about some of the work that people in my group and others extended people have been doing related to provable security in AWS. So as the scale and diversity of cloud application is increasing, as well as the evolving security requirements, is really driving the next generation of tools and technologies in AWS, where we are trying to say, how can we automate checks around security so that others don't have to worry about it? And others can include enterprises, they can include startups, they can use individual users, universities, academic users, the whole spectrum, so that they don't have to go and keep doing this undifferentiated heavy lifting around security and compliance. And this is what I feel is turning security from an obligation to an advantage. So what are some of the types of questions people have that they want to know whenever they are setting up a cloud environment? Who has access to my resources? It can be storage, compute, analytics, and questions such as, who can SSH into my box? Who can SSH into my EC2 instance? Access control around secure things, access control just around general things. You have things separated into private and public elements. The goal here with this work is to say, I want a secure cloud environment, and yes, I can mathematically prove that it is secure. So AWS has this shared responsibility model. So I'll talk a little bit about what that means. It means AWS is responsible for security of the cloud. It is responsible for providing security of the infrastructure, of the hardware, of the software, and the networking components. And the customer is responsible for security in the cloud. So what is it responsible for? Well, it depends on the types of services that they are using. They're responsible for configurations of the services. They're responsible for management of the services, patching the guest OSs. So I'm not going to focus a lot of my talk here of what work we've done regarding with provable security in security of the cloud, but I did want to mention a couple of things. What are some of the things we are looking at? We are looking at how can we verify that the boot code running on AWS data centers is free of any is memory safe. So this is work that says, oh, all the boot code that's running in AWS is memory safe. Another part of the work, we saw a talk earlier about TLS. So S2N is an open source TLS implementation where there's various properties that have been proved, including its HMAC implementation. And a key part of this is to say the proof infrastructure is continuously checked during the entire lifetime of the software development, so that you know that as the software continues to evolve, the properties about it continue to hold. So when I talked about the shared responsibility model, AWS is also trying to provide tools and technologies, and we are looking into how can we do provable security to help customers and to help users be more secure in the cloud. And that is where I'm going to focus most of the talk today in, is talk about a couple of initiatives that we have for providing provable security in the cloud. Here's what an EC2 network looks like. What we have is we want to automatically answer queries about EC2 networking configurations. We don't want to, but we want assurance. So there's a technology that we are developing that performs a static analysis of the network. There are no packets that are sent. And then we create a logical representation of this model to reason about network semantics. And so once you get a question, you have provable assurance that yes, it is the case that there is no path from instance I to instance J. Another example is access control policies, which you attach to users, identities, resources. This controls who has access to what resources. And we want to say that we want to have an ability to automatically reason about these as well, because we want assurance. We want provable assurance that only the people that I want access to my access control, to my resources, are the ones who have access to those. So I've talked a lot about provable and logical and analysis. It's all founded in logic, which is introduced by an English mathematician named George Boole in the 1800s. So how are we taking the foundations of logic and applying it to how we are doing provable security? This is a simple math equation. Everybody says, you know, here's three variables, 3x plus 2y minus z, used in an expression that's greater than 4. We can ask, this is a well-formed, well-known mathematical foundation. We can ask questions of it. We can ask question, does there exist an assignment to x, y, and z such that the expression on the left will be greater than, you know, the constant on the right? And the answer is yes. There exists many such assignments to x, y, and z. But we only ask the question, does there exist one? And if it doesn't exist, we want an answer that says, no, this expression is unsatisfiable. There is no assignment to x, y, and z that will ever make it true. So we want to ask those same foundational questions to our EC2 networks. We want to ask, does there exist any assignments to my security groups, to my ACLs, through my IP addresses that will allow me to get from point A to point B in my network? So why is this complicated? Because there's a lot of things to consider. If you look at what consists of the networking components in an EC2 network, there's about 30. You have your VPCs, your subnets, your route tables, your ACLs, your peering connections, and it's a combination of those that determine access. And this is what a network looks like in real life. It's big and it's complex. It's hard to reason about it manually. It's hard to say, oh, I'm going to just look at my infrastructure definition and figure out whether or not I have access. It's not a process humans are trained to do. And I want assurance. I want to say, are there any instances that are tagged private that are accessible from the internet? Because you want to have a case that it never happens. So why can't we just do some testing? Couldn't we brute force this problem? Let's see what would happen if we did try to do that. For all instances, for all security groups, for all ACLs, for all subnets, for all route tables, for all VPCs, for all peering connections. And you see where I'm going. This combination is going to blow up in our face. We're never going to get there. And today, there's over 30 networking components in EC2 alone. So how do we make this a more principled approach? How do we take things that are well-defined in math and apply it to the real, more complex, less structured real world? This is where we use something called a decision procedure. A decision procedure is an algorithm that takes a decision problem and gives you a yes or no answer. The trick here is to take your real world problem and model it into one of them as a mathematical form that a decision procedure understands. So is it a harder problem or is it an easier problem? So think about math, think about natural numbers. Natural numbers are countably infinite. Real numbers are uncountably infinite. But computers are finite. So representations on computers are finite. So this is what makes it more tractable, where we can take a real world problem, and if we model it as a math problem, now we have the theory of bit vectors, because your integers are 32-bit or 64-bit. You have strings, you have linear integer arithmetic, but it's all bounded. So we turn a problem and make it decidable. So this is where we can leverage the power of math, but apply it to real world problems. There's been a lot of engineering been done in the past 30 years to develop tools and technologies that can take and actually solve these problems very quickly. Some of these examples are Z3, CVC4, Monosat. These are all open source tools that you can go and download and try to encode your problem as a mathematical logical formula and have one of these solvers solve it. So now that we have a foundation, how do we get from there to ask the question, did I build the network I intended to build? And I'm going to give a bit of a preview of how we do it for this service that we call Tiros. Here is a simple example VPC. It has EC2 network. It includes a VPC, a subnet, 2 instances. Both have ENIs, the networking interface attached to it, as well as a security group, a router, and an internet gateway. And I want to ask the question, can I, a random person on the internet, SSH into instance A? So the first thing we need to do is transform this network into a model, in a mathematical model that we can reason about. So we are going to build a symbolic graph from this network representation. So given 2 instances, we are going to have 2 equivalent nodes in the graph. We're going to have nodes that represents the ENI, the network interfaces as well, so going from the instance to the network interface. They both are part of that same subnet, so we have edges going to the subnet. The subnet is part of the VPC, but the subnet also connects to a route table. The route table has an outgoing edge to the internet gateway, and the internet gateway has an inbound edge to the VPC. And the internet gateway is how we communicate through with the internet. And then finally, we have the security groups that are attached to the ENIs, the network interfaces. So this is part of the symbolic graph. We have transformed each of the elements in the VPC network to nodes in our symbolic graph. The next thing we do is add constraints. So traffic can only flow from the VPC to the subnet if the destination address is within a certain CIDR block. So that is a constraint that we add along the edge going from the VPC to the subnet. Another example where we have the subnet going to the network interface. Here, the destination address has to be a specific value, as well as the source address has to be within a certain CIDR block range. So we will add these constraints on the edges across the whole graph. So now we have a constraints problem, and we have a mathematical formula that represents our EC2 network. So how can I go and ask this question? Can I SSH into instance A? The way we would do it is first encode the question as a logical formula as well. So here it will say the destination port has to be 22, the source port has to be greater than or equal to 1024, the protocol has to be 6, and there needs to be a feasible path from the internet to instance A. And we will ask this question, we will ask these solvers this question on this symbolic graph that we generated. So this generation happens automatically, so there is no manual intervention required. And the answer is yes, there does exist a path from the internet to instance A. And what this means is there is a set of values which you assign to the constraints along this path that will make this true, that demonstrates the feasibility of this path. So where do we use this? It can be used in a variety of applications: compliance, application security, incident response. Imagine you have an instance that gets compromised in your network. You know that you're part of an incident response team or a security team. What would you do? You want to know what's the blast radius. Now that I do have a compromised network, where else can I get to from this network? Application security. There's restrictions about who needs to have access to what. If you have third-party contractors on site, maybe there's parts of the network that they should not have access to. Compliance, the compliance regime. One example is PCI. So for a lot of companies that hold customer credit card information have to comply with PCI regulations. There's 8 network-based controls in the PCI standards that define how data should be stored. So here's a sampling of what those are. One specific one says, oh, restrict all inbound and outbound traffic to that which is just necessary for the cardholder data and just deny all the other ones. So, question, right? How can I use it? You can go to AWS. There is a service called AWS Amazon Inspector, and it has a set of network reachability rules. And they are all driven by this, the logic that I was talking about earlier, called Tyros. It goes and creates a snapshot of your network. It'll do these describe calls and create a network topology, and based on its understanding of the EC2 networking component semantics. And you don't have to specify the rules. The rules are prepackaged. The questions are prepackaged. You can go in there, turn it on, and ask these questions. Another example of how we can use provable security is using similar mathematical models to answer questions about access control policies. Here we want to answer the question, given that I have a JSON-looking access control policy, is it the case that only authorized users have access to sensitive data? And often, it's not just a single policy that determines access. So if there are people, if you have worked in the AWS ecosystem, will know you have SCPs at the organization level, and then you have identity policies that are attached to users and roles, and then there's policies attached to resources. And what is allowed or denied can be a combination of those sets of policies. So here's a very simple policy that could be attached to your S3 bucket. Here it's saying, allow a certain principal, any action that is not S3 delete on this resources if the requests come from a source VPC. And on this, I want to check that no principal can delete my bucket. That's the thing I want to check. So again, couldn't we just test this? What's the problem space? Under approximation would be, I have 10 to the 12 AWS accounts, 5,000 actions, 10 to the 13 resources in AWS, and essentially an infinite number of condition keys. This is just to show this is not a problem that we can brute force. But we can turn it into logic. This is a very natural transformation, even simpler one than the one we saw for VPCs. Here you can say, oh, this principal equals this, and my action is not equal to S3 delete, and my resource is a bucket, and the source VPC is a given value. And I'm going to transform my question into logic as well. I'm going to say, ensure that no principal can delete my bucket. So that's going to turn into, oh, make sure that there is no principal star such that the action is S3 delete star on my resource. Given the logical representation for my policy and the logical representation for my question, the solver can give you an answer. Oh, this is compliant. Now what happens if I make a small syntactic change? Here I'm turning the principal into not principal and the not action into action. And I would make the equivalent transformation in the logical representation, and the answer is not compliant. So the idea here is seemingly simple syntactic changes can have a larger difference in the semantic meaning of what you're checking. If you want to learn more about it, we have a blog post that dives into the use cases about where it's used in the different services and what's under the hood. If you want to dig even deeper, we have a technical paper published on this that talks about how we take the AWS policies and turn it into logical mathematical formulas that are known as SMT. And one place that it is used is S3, a storage service that AWS has. If you go to the S3 console, you will have a badge, an orange badge saying, is your resource publicly accessible or not? So this is driven by the same technologies, Alcova, that I was talking about. We have a definition of what consists of making it, what consists of defining whether the bucket is public or not. So I've given a couple of examples of how you can take core parts of the infrastructure and have assurance, mathematical assurance that yes, this is the case. It's not fuzzing, it's not testing, it's not sampling, but going through all possible scenarios. So in case of policies, it evaluates all possible request contexts, not explicitly, but symbolically. There's use cases in across the spectrum for all industries, whether it's financial services, technology companies, media, or publishing. And we are including more and more parts of our infrastructure in providing this provable assurance that we call it. All the papers that I presented glimpses of, and for details, we have a Provable Security webpage. You can also just search for AWS Provable Security, and you will get to this. And I'm happy to take questions.